Okay, so welcome you all. My name is András Hajdu and my colleague is also here, Dr. Balázs Harangi. And as Levente mentioned, he likes DeepL very much with you. So yesterday we just translated the whole PPT slides using DeepL within 1 minute. Then we also did a human check, but please forgive us that there are some bugs regarding for the words, so not everywhere we was able to find the bugs. So sometimes the translation was not perfect because we realized that we should try to translate it to English. Yes, as Csaba mentioned, that this talk will be about medical image processing. At the University of Debrecen, we have a very strong medical school as well. So we have many projects for a long time with this medical school. And now the topic what we brought here is a bit more practical in some sense. I will just very shortly show you the methodological aspects as well. So some theoretical parts, let's say, so I would say a bit more interesting regarding scientific issues. But as I told you, I also would like to show you the practical issues, the practical problems, because nowadays we are facing them. Sometimes it's very tricky to solve these problems, especially in the medical domain. Okay, so what I will show you, that basically it's a screening system which is developed for the medical domain, and this is the cervical cancer, which is a women disease. So basically this is a cancerous issue regarding the uterus for women. If you are not so much experienced regarding these problems. So basically this is the problem whether we are able to recognize at cell level the cancer. And if I will have time, I don't want to take too much time, especially I don't want to ruin the coffee break, so I think we don't have too much time. Shortly, if I will have some minutes, I would like to show you that besides the image processing approaches, of course, we also have to take care about the large language models as well. So in this medical domain, somehow the combination of the image and the text data is essentially important for us. Okay, so basically what is the whole project is about, you can see here, it's quite common, so it's not so difficult. We have whole side images, so we have a 3D histag scanner. So basically it's about pathology. Here you can see that basically we scan a smear, and then basically we will have such smaller parts of the image. So we slice the smear after identifying the region of interest. So basically just forget the background. Then we subdivide it into smaller segments, the images, and basically it's quite easy to say, so what the problem is. You have to find possible cancerous cells among all the cells in the smear. So basically this is how it looks like. And otherwise it's not a big deal, because you can think about a simple classification, object detection stuff. So you have a classification problem here. You have to detect all the single cells, and then you basically have to feed it to any simple object detection approach like YOLO or anything else, and you have to make the final decision. It was a project with companies, so we can say we are award winner. So because we received this Hungarian Innovation Prize this year, and we can also go for a grand prize. But it was said that first we have to show that the system is able to make financial income as well. It means that somehow we should introduce it into the Hungarian healthcare system. So we are now about how to introduce it. Basically, we are close to finish the project also in this sense, but it means a very exhausting testing first. It takes a lot of time. I will show you the details, but basically this would be the last step, and hopefully we will be able to integrate it into the Hungarian healthcare system in the end. So this is our main aim, finally. Okay, so my main point will be about basically how the data set was created. And shortly I will show you, of course, also what type of image processing techniques can be used for semantic segmentation also, and also for classification, object detection. But I think that the most important and most interesting part of this whole activity, it was mainly how to put together the whole data sets. As I told you, we need, of course, some kind of preprocessing steps. Then we have to take care about, again, how the annotation is created, how the training set, test set, evaluation part can be created. So basically, I would like to show these points now shortly. And then, of course, the second part will be the testing, the prototype, which is now under consideration. So which is done at the moment also. So to try to integrate it into the healthcare system in the end. Okay, so basically we are talking about these smears. They are called otherwise Papa Nikolaou smears, and what you have to know about these smears, the digitized images, that there is a technique, but it's quite expensive, to clean a bit more these patterns, the cells themselves. So if you apply some kind of liquids, then you can have very, very nice images. So it's very easy then to make the difference between the cancerous and non-cancerous cells. Unfortunately, in the Hungarian practice, you can find these methods mainly in the private sector only. So we have to pay a bit more for that. So the challenge here is that the pattern, the input pattern, is not so nice. So it's quite dirty in some sense. So it's much more challenging than to go for the clean patterns. Okay, so basically I can go step by step. So this was the starting point. So we received these smears from the pathological clinic. So you can see here that manually annotated those parts where you can find perhaps positive cells, so cancerous cells. Otherwise, if we don't have this input, then the database can be very much imbalanced, so there won't be any cancerous cells otherwise, because of course they are quite rare. So we have to take care about to have many positive samples as well. Even with this approach, still it's unbalanced, so we have much more healthy cells, of course, than positive ones, but this was the input. So manual annotation like that. You can see here the whole smear. It's huge otherwise, so definitely big data issues everywhere all around this project. But this was the input. So we went for the manual annotation first. So we had a group for annotators. They focused on these regions because these regions you can expect to contain both negative and positive cells as well. So basically this was the input. I don't want to go into the details, but here you can see some figures, so how large the data is. Something like 6 gigabytes on average digitized smear is, so indeed it's quite a large one. Then it was subdivided, as you can see, something like 5,000 sub-images. Each image has 2,000 times 2,000 resolution, so they are quite huge. I don't know exactly, but I think definitely at least few thousand cells on each square to evaluate, and we have to check each of the cells in one smear. So basically this was the input. You can see here very simple pre-processing steps. First, so how to focus on only those regions that are more interesting, and then we asked the annotator just to focus on those cells, including in these important or hopefully more important parts. So this was the first step. So how to create a manual annotation for these specific image parts, and we developed these cells everywhere are manual annotated pixel level, so semantic segmentation issue. But as you have already seen, we don't use at the moment semantic segmentation because we just want to make a classification whether a cell is positive or negative. So simply a bounding box containing a single cell, which is the input for now our system. But first, since these cells are manually annotated at pixel level, we have created a semantic segmentation process first, as you can see here. In this way, we are able to separate the cells, and then we are able to try to have a bounding box for each cell separately. And this can also later, so the first step for the annotation was to try to separate the cells in bounding boxes, and then to ask again the clinical experts to say yes or no for each cell, so to make the secondary annotation for the classification task. And as I told you, we used here, usually we use ensemble-based methodologies. which can be used also here. In semantic segmentation, you can use many different types of CNNs and so on. You can use different type of fusion combination for all these semantic segmentation algorithms. So we do quite a lot of research in that field, but I don't want to go into the details. So how we aggregate, you can use different type of aggregation functions. You can use skip connections, residual connections. You can do whatever you want. So there are many approaches to try to improve semantic segmentation. Here you can see few results that finally we were quite happy with the output, but as I told you, we use only semantic segmentation just to prepare for the image classification task and image classification labeling the input images. Later on, of course, it could be an idea to go for morphological better features and characteristic features to make the final decision, but at the moment we simply use Euro-like classification approach to make the final decision. So we don't go into the semantic segmentation level. So basically this is what happened, and okay, I think I can skip now. So basically this was the output, that a cell, each cell was separated into a separate bounding box, and we also developed cell annotator tool for the medical experts, clinical experts, and they had to classify these images, of course, positive, negative. We had also other classes like nothing or garbage or something like that. So there were also some more classes when it was not possible to recognize the original image. Okay, so basically this is what we have done as for the annotated cell image dataset. So as I will show you, we have now two datasets. One dataset which is semantically segmented. Basically there is no label for this dataset, but very precisely a lot of cells segmented semantically pixel level. And we also have a secondary database which contains cells in bounding boxes, and they already have the label, whether they are positive, negative, or something else. Here you can see basically the size of the data set. You can see also the unbalanced stuff, so of course still more healthy cases than unhealthy cases, and so on. Of course we can use different type of techniques to get rid of a bit with this imbalance problem, like augmentation, nothing special. So of course we also consider all these possibilities. Of course you have to take care what type of augmentation can be used here, rotation and so on, sharpening and so on. Not everything, of course. Okay, so this is, I think, quite important. So what is the size of the data set? Here you can see, so we had digitized smells with markings 363 altogether. You can see here the size, and now the exhausting testing is something we would be very happy to have the final results after 10,000 slices. So after that, if we have quite a good accuracy, which can be accepted by the authorities, then it is possible to integrate the whole stuff in the healthcare system. Here you can see also how many manually annotated cell images we have, and which is a good news that we are already able to publish the data set. We use the scientific data journal for that purpose. And now, as I told you, we can say it's already accepted. There was an answer requirement for minor revision only. It is the semantic segmentation part, so which is hopefully will be available very soon. So this was one paper, and we have definitely an accepted paper for the second type of the data set, where the labeled cells are released. Okay, and this is the testing part, as I told you. So it's indeed a very exhausting test, because 10,000 very large images should be classified. We will do it at cell level, so of course it can be a question. It's a small research that how to decide how to make a final decision at small level, because we have the decision at cell level. So of course we have to create a simple neural network or simple statistics to make a final result after the cell level decision. So what to say for the whole smell, so for the whole case. Okay. this is what is considered for testing. Otherwise, so testing the prototype, here you can see basically, so I will show you that this is what we have reached so far. This is 2 examples only, but it shows you that there are 2 smear examples here, 2 different smears. The solid colors show, I think, the decision of the system, and the experts, the human experts, are shown by the not solid part, the lighter part. Basically, it shows you that if there are, of course, positive, negative, and neutral cases, let's say so, then basically we can say that the system is basically able to recover the same, of course, not in the same, exactly in the same amount like the human. So let's say we are optimistic that we will have quite a good final outcome. Okay, this is still about I think the testing the prototype, and this is what is, of course, also can be a very easy final outcome. So we are able to show what we have found for the clinical medical experts. It can be also good for education, of course, because we can say that this is a positive case, this is a negative case, this is a rubbish case, and so on. So, of course, not only for screening and for decisions, so it can be also used as decision support. So we are able to visualize, of course, also the suspicious elements of the components or suspicious areas in the whole image. Okay, very interesting, of course, all the time for a practical issue what the human says. So we also try to check what about the human experts. All the time very interesting. We had, for example, here 3 experts, and we were, of course, curious what they say for the different cells. It was simply healthy, non-healthy, or something else. And basically, this is the important. These are the important figures. Here you can see that when 3 experts were asked to say something about different cell images, here you can see that something like 75% when all the 3 experts said the same, but 25% when only 2 said the same, and we had something like 1.3% when they said completely different stuff. So it's very difficult, of course, to evaluate regarding the clinical field, regarding the expert's opinion, so what exactly to state in the end. Of course, it would be very nice. So basically, this shows you that it's very difficult to have a nice ground truth. So it's not only about metric, how to measure the accuracy for, I don't know, cell detection or semantic segmentation, but it's very difficult to have something like golden standards or ground truth for an image data set. So to be honest, we cannot be completely sure whether the image data set contains correct labeling or not. We just hope. But I think we don't have a better choice at the moment. Okay, and basically this is what I wanted to show you. So that's why we are quite optimistic. The F1 score is quite okay. We will see in the end, of course. So we are also curious what will be the final outcome, but hopefully the system will be quite accurate. Very exhausting testing is needed. We have an NVIDIA server contains 8 A100 GPU cards. Now we are purchasing a new one, H100 cards. So we will have 2 NVIDIA servers, DGX servers, hopefully in the very near future. And it was very important again for optimization, because we started with 90 minutes for one smear. Then we could able to reach something like 50 minutes per smear, and now we are able to do it in 7 minutes, I think, for one smear, which is quite close to the human speed. I think we are now faster than the human speed for making a decision. But it was very important, for example, that we had to copy all the sub-images into the GPU first, then we applied YOLO, which became faster. So there were several such implementation optimization issues as well. As I told you, we have 2 papers now with scientific data for the data set. Otherwise, we have several other papers for the methodological part, so how to do the semantic segmentation, object detection, and so on. And one point that can be interesting also for you, that we are thinking about to launch an international competition. We are thinking about, for example, the International Symposium for Biomedical Imaging, so our international conference, because we retained unofficially we retained some parts of the data sets. In that way that we will have a test data set, annotated test data set. So we are very happy if you are interested in participating in this competition. So hopefully we will be able to propose this for an international conference in this summer. So we are very happy if there will be different teams, or also if you have any ideas about preparing the metrics, preparing the data set, and so on. Hopefully we'll be able to release it soon. Okay, and as only 1 minute for this language processing part, I think it's very difficult now to handle the medical assets. We are fighting all the time with the medical school because, as I can see also in Hungary and also in other countries, all the medical schools try to not to publish their medical data sets. I warn them that if they wait too much, then if the generative methods will be too strong, then all these data sets will not be useful anymore, because for other data sets, the generative methods will be able to recover all these data sets. So as for me, they should be released as fast as possible. Very shortly, we have PET images, for example. Here we do something like, again, segmentation, or we try to find tumorous, cancerous areas in the PET images. And here we can use, for example, medical records parallelly, simultaneously, and then, for example, we can support the annotation work with saying that there is a lesion somewhere, and there is a lesion somewhere. This information is coming from the medical records. And here you can see a medical record. It's nothing special. LLMs, we can also use our own LLMs running on the NVIDIA server. So we also use pre-trained models, but also fine-tuning we are doing, and so on and so on. We can use quite large language models now, and then you are able to, for example, support the annotation, because you will be able to find better what about the lesion size, so you can find all these lesions better in the image data. Okay, so basically that's all. Thank you very much for your attention.